Sorry about the room change last minute. If any one of your friends is supposed to be here and they're not here, you might want to message them and be like, hey, we're on the 8th floor. Cool. All right, so this is Awesome Deep Learning. Quick show of hands. For who is it the first time that you're at one of our events? 50-50, like always. Wonderful. Okay, so just going to go over some basic stuff, then we'll jump right into the talk. So if you parked in the garage downstairs, ask Elijah for validation. He's not currently in the room right now, but he'll be back soon. But definitely on the way out, you can ask him. If you don't find him, just look for me. You have to have arrived after 6 p.m. and leave by 10 p.m. And if you do that, it's about, I think, $8. Otherwise, you don't want to know. So we meet on the first Tuesdays of the month. We will actually not have one next month. We don't usually have them in July. So we'll have one again in August and henceforth. We like to be focused on research, new breakthroughs, or even implementations, novel implementations, anything that pushes the needle onto the next great thing. And this, in terms of culture, we're open discussion, collaborative. This isn't just a one-to-many. It's also a great chance for you to say, hey, I actually know something about that. Just raise your hand. Or if you have a question, something's not clear, just raise your hand. I'm going to be seated over there, herding all the cats. So, just ask, and I'll make sure you get heard. Ignore that. Okay. So we're just going to jump into the presentation. Mr. Joe Fioti here will be presenting. Great. Thank you. Everyone, welcome Joe.
President here going to order you to war or something.
What are your orders?
War 3, here we go. This talk is, I'm Joe. I'm the co-founder of General Cognition. It's this new little startup. My co-founder Hassan and I started. And our mission is to do a 40-hour work week in 20 minutes. It's a little lofty, but we're going to talk today about one of the key tools that is helping us get there, which is a library I started writing last year called Luminal. The little tagline is deep learning at the speed of light, but we don't actually go at the speed of light, so it's kind of a lie. But this is about our startup. It's at gcog.ai or generalcognition.ai. And really what we're trying to do is do large language models on MacBook Pros at speed. That's sort of part of our assistant. And in order to do that, these things are huge. They were they didn't even exist a couple of years ago because they were too big. And now we're trying to run them on mobile hardware, which is very difficult. There wasn't a ready-made solution when we started this. There really still isn't. So we had some goals for really fast speed, really good deployability, and really good extensibility, because we want to bring this to NVIDIA GPUs, to Metal GPUs, and eventually, who knows, photonic processors or quantum computers, whatever. So, jumping right in, I assume most of you are somewhat versed in the basics of deep learning. That's basically the data we work with. It's tensors. It's just multi-dimensional arrays. Anything over 2 dimensions usually is referred to as a tensor. And if you think about it, deep learning is actually just really simple linear algebra. If you can do matmls, adds, and like a couple other element-wise operations, you can run every modern model out there. So LLMs, convnets, diffusion, pretty much any headline model now. So with that being said, why are deep learning libraries so complicated? They have no right to be. So PyTorch has over 200 operations. It has over 15 different data types. It also runs on a ton of devices, and you have to think that the number of operation implementations they have is 200 times 15 times the number of devices they have. So that multiplicative factor sort of explodes the number of implementations you need. So now, as a consequence, PyTorch is over 3 million lines of code. And understanding that is a full-time job, which severely limits how much innovation you can do, the approachability of the framework, and TensorFlow is much, much worse. So it doesn't get better. So since I said that deep learning is actually really simple linear algebra, how simple can it be? We actually can boil all these major models down to a couple simple primitive operations. And so I listed them out there, just some like element-wise operations, some adds, moles, some reduce, stuff like that. Those aren't example ones, those are the actual primitive operations in Luminal. So every Luminal model boils down to those simple primitive operations. And with those, we build up Llama, Whisper, we could build up Diffusion, and yeah, pretty much all the favorite models. Is that really it? I mean, you didn't see subtraction on that list, but it turns out you don't need subtraction. Subtraction is just a minus b is a plus -1 times b. In the same way, once you have reciprocal, you can do division. So a times reciprocal of b. It turns out you don't even need mapmul, which is usually a staple of deep learning libraries. You can just do sum reduce, and if you can do some fancy shape movement stuff, you can basically expand the two operands and then do a sum reduce, and it's equivalent to a mapmul. The same thing works with convolutions. So all of the primitive operations that are in PyTorch or TensorFlow actually boil down to even more primitive operations. And it turns out that one of the main reasons PyTorch needs to be so complicated is because it treats everything dynamically. So Python is known as a very dynamic language. You can basically do anything at any time, put print statements wherever. But it turns out that deep learning models don't need to be that way. They don't need to have if statements or for loops. You can actually turn most of these workloads into just static, directed, acyclic graphs. And like we said, we're just using simple operations. So you can build these graphs out of simple operations. So in front of you, you see a linear layer. You have the input coming in on one side, the weight coming in on the other. There's a multiply and then a sum reduce. That right there is just a dense layer, and then you can stack a lot of those. And what you see on the right side here is one layer of Llama. So yeah, multiply that by 32, and that's the smallest Llama. So these graphs get pretty unwieldy. So what are the consequences? Why even do any of this? Well, you get extreme simplicity, like I talked about, and Luminal core is under 5,000 lines of code. It's really easy to understand. You should be able to understand it in an afternoon. I'd like to think the code's fairly well written. It's not at all fast, though. That's the main problem. So if you boil down all of these operators into tons and tons and tons of primitive operators, you get very, very terrible performance. So Llama 7b, I think it took me about a day to get a small sentence out of it when I ran it the first time on my laptop. Yeah, about 2.5 hours per token, so I don't think you're going to be raising any money with those speeds. But it turns out that we can salvage this, and we can compile our way to high performance. So compilers really are the pièce de résistance of Luminal. It's the reason why this all works. So we shouldn't actually run the primitive op graphs. We talked about how slow they are. Nobody's expected to, and so what if we made little programs to take in that directed acyclic graph that describes the network, transform it into some faster computation, and then run the faster computation. Since our entire network is fully characterized by that directed acyclic graph, we can do that in a very bounded, simple way. And it turns out that, what do we call programs that turn slow computation into fast computation? Generally, they go by the name of compilers. That's not the only thing compilers are, but that's what we call them in Luminal. So we can apply some compilation generically. We have like very simple, straightforward compilation optimizations here. So we do common subexpression elimination. That's what you see on the top there. Basically, you have an input tensor, and then you have an exp, and then a sign, and then on the right you have a square root. And it turns out like you don't need to do exp twice. So a compiler goes in there and eliminates that. You can do arithmetic simplification. So you have an exp and a log. those are complementary operations, so you can just delete them. If any ops are unused, they can get deleted as well. So simple stuff like this can actually make a big difference, and this can be applied before we do any device-specific or model-specific optimizations. So they're very robust. But we never talked about devices. So I said PyTorch pays a huge complexity price for using all these different devices, and you can't actually get away from the devices. You need hardware. So where do these go? It turns out you can just use compilers to directly translate one-to-one each of those primitive operations that we listed into device-specific primitive operations. And then since you have the full graph characterized at compile time, you can insert copy to and copy from device calls so that your data moves correctly. Whenever you're running the model, it's going to copy the inputs to the device, and then at the end of the run, it'll copy the results back, etc. So that's how we support devices, and then we can get into how we support data types in the same way. So data types are compilers as well. You're gonna sense a theme happening here. Everything's compilers. So it's we basically compile to a certain device and a certain data type. So for that example there, we do CUDA. So we're compiling to NVIDIA GPUs. And then we're compiling to half precision in this example. And what we're able to do is, since we know this all at compile time, we can create the kernels on the fly, the GPU programs on the fly, specifically targeting the data types we want. So we don't need to hand write out all of these different data types to target all these different, all these different kernels to target all these data types ahead of time. And then, since this is all planned out ahead of time, mixed precision works very well because you know ahead of time what operations have numerical instabilities, and then you can just internally switch the precisions around within the graph. So that's how we're able to handle data types. And by the way, because those devices and data types are separated by different compilers, then you're able to avoid that multiplicative explosion of complexity, because the number of compilers you need is the number of devices plus the number of data types, not the number of devices times the number of data types. But how do we actually really go fast? So NVIDIA has about 10,000 engineers, and they all write kernels for a living. We're not going to think that we're better than them. I don't have that much hubris. So we want to target their libraries that they give away for free. Kublos is a popular NVIDIA GPU library, and so they do really fast matrix multiplication. Instead of trying to write our own matrix multiplier, we can have a compiler that just looks for the pattern on the left, and then it swaps in a matmul op that calls Kublos on the right. And because it's by pattern matching, if you ever have that similar pattern, even if you didn't mean to do a matrix multiplication, the compiler will find it and put in the most efficient operation for the job. So one of the main ways you go fast, though, is by doing something called kernel fusion. 99%, probably around 98, 99% of energy spent in GPUs is just moving data around. About 1% is on compute, so if we can move less data, we can go a lot faster. The most straightforward way of moving less data is doing more with the data when it's on the compute side, when it's at the compute element. And so one of the ways that people do that is by fusing together different ops into the same GPU kernel. And so, for instance, if we're going to do an sine and then an exp2, those are usually traditionally two separate kernels. And you sort of see on the right image with the left-hand side of the right image, you see the two kernels there. And in this case, SM stands for streaming multiprocessor. HBM stands for high bandwidth memory. So the blue is the memory, the green is the compute. And we have to load all of the data to the compute for kernel A, then we write it back to bandwidth, to memory, and then we read it back for kernel B, and then it's not shown there, but we have to write it back, of course. Instead, wouldn't it be great if we can just do both operations in one kernel, and so we can only have one read and one write? And so we basically take two different fusible ops, two different element-wise ops, and we can put them together into one kernel, and then only read once and only write once. And so we get this sine exp2 kernel on the right there. And that's all done dynamically, so it turns out that you can like take this really far.
Wait, hang on. Can you go back? Yeah, I had a question. So is this all related to flash attention in a way?
So flash attention is an example of an extremely fused kernel.
Who here knows about flash attention? Just raise your hand. Okay, good number, y'all. Is it okay if you just go over?
Yeah. So flash attention is, well, it's a very complex kernel, but basically during attention, what you want to do is you want to take your queries, keys, and values. You want to do a matrix multiplication of keys times queries, which then gives you a score, basically, of how much you should attend to each value. And then what you want to do is softmax that so that all the probabilities, all the scores sum to 1. And then you want to multiply all those scores by the values. And so you get like a weighted average of all the values. Normally that's done in the exact way I said, so it just is explicit separate calls. What the geniuses at Stanford figured out how to do is fuse them all into a single kernel. And so instead of doing a matrix multiplication, a softmax, a matmul again, they figured out how to do softmax inside the kernel and combine that all with the two matrix multiplications. And so you have a single kernel that launches now versus doing all this sequential work. And so that ends up being, I think, something like 5 or 6 times faster than just doing it all in a naive way. So pretty much everyone needs to use that.
So just to get everyone on the same page, flash attention, like you said, is an engineered optimization for the attention mechanism. And the attention mechanism is a core driver for transformers, which are the core drivers for LLMs and all the great Gen AI stuff we're seeing. So there was, these researchers spent a lot of time finding out something that just works. And there's, a decade after that of optimizations. And flash attention has been one of those things, and these guys here at General Cognition are doing is taking that same approach and saying, hey, there's a lot of unoptimized territory for us to go grab, fuse these operations into fewer sequences, or shorter sequences, and you get back a lot of that time, and so you can do more with less hardware.
Yeah, and flash attention is an example of something that, like, I don't know, hundreds or thousands of PhD hours were spent discovering and writing by hand. And so what we really want to do, the end goal here, is to get the machine to figure out and discover something like flash attention by itself. And if it can do that, it can discover really efficient ops up and down the model everywhere, all these different kinds, and then the PhDs can take a nap. So yeah, this is an example of just how far you can take kernel fusion. So on the left-hand side here, we have a bunch of individual operations, and they're all fusible. And our compiler essentially found the one on the right-hand side of the operation. Now, I think I actually don't know what operation, what model this is from, but yeah, it basically fused like 6 or 7 different operations into one kernel, and so it only does 2 reads for each of the inputs and 1 write, instead of, I think it's something like 15 or 20 reads and writes on the left-hand side.
We have a question?
Yes, so your compiler found that based on the 11 primitives?
Yeah, so on the left-hand side you see these are some of the 11 primitives there, and they all operate just, at least in this example, on single elements at a time. So, take sine, for example. It's like you have a tensor that comes in, and what you do is you take the sine of each element, and then you output the tensor. And so it's sort of like a one-to-one input-output. If you have other ops that work the exact same way, you can just sort of stack them on top of each other, write them into a kernel, and then compile that kernel. And that's what we see on the right-hand side here. So you save tremendously on bandwidth.
What about Onyx? Do you guys?
Yeah, so Onyx is a storage format. So you basically have like all these different neural networks from all these different frameworks can sort of be represented in this storage format, which represents the computation. What we have as an extension is the ability to read those files, those representations, and then we sort of convert them into the primitive graph that you see on the left-hand side there, and then we run all our compilers on it. So we basically bring Onyx graphs into the common language that is our primitive graphs, and then all of our compilers are fair game and work on them.
So what about the Onyx optimizations that do some of the same?
So we do most of the same things that Onyx runtime specifically, I think you're talking about, does. Like Onyx runtime is a specific way to run the Onyx graphs. So we do a lot of what they do basically, but we're able to do more because we have a simpler offset than Onyx. Onyx has, I believe, something like 50 or 60 different ops. So yeah, our compilers can be simpler. Good question.
Do you make multiple passes over the code, or is it able to do it all in one shot?
What do you mean?
Well, you're able to get the graph from the left to the right.
Oh, yeah. So we do a bunch of passes. I think the typical end-to-end compiler run is probably something like 100 or so passes. This kernel specifically basically just loops through the graph and looks at all the fusible ops and then keeps trying to fuse them until it does a whole pass over the graph and can't find any more fusible ops, and then we assume the graph is fully fused. But yeah, we do many passes over that graph.
One more question on this line. Is there a general sense then that the graph unit is actually the minimum possible graph, or are there paths that generated a more optimal one?
No, there definitely is. And so basically what we're operating on here is a combination of heuristics and some automatic discovery, but there definitely is like more optimal ways to represent this, and I'll touch on how we're getting closer to that at the end of this. But yeah, we're definitely far from the most optimal. So I talked about how memory is expensive to read and write from in terms of time. It's also expensive just in dollars. It costs a lot, and Jensen charges a ton for VRAM. So we want to minimize and reuse memory as much as possible. Because we have the whole graph specified at compile time, we know exactly how much memory our model is going to use, and we know where to allocate different bits of memory. And so we're able to statically optimize how much memory we're going to use ahead of time and where we're going to reuse memory. And so in this case, like what you see is we see 3 storage buffers, 2 operations in green there, 3 buffers in blue. That's the naive way to do it, and you have all of the intermediate outputs stored in their own buffer. Each of those buffers are little pieces of memory. But it turns out that like once you're writing to buffer 3, you don't actually use buffer 1 anymore. And so you can, as long as they're the same size or they're correctly sized, you can reuse that memory. And so we have another compiler that goes in there and just ties these ops together. They tie these buffers together, and so we can optimally plan out and reuse memory. And that is somewhat close to near optimal. Another way to really speed up and get a lot of performance is by limiting the amount of time you have to talk to the CPU. The CPU is very slow, and that sort of one hop is from GPU to CPU takes a long time, and so you can really see that add up on the left-hand side here. You can see that launch A, launch B, launch C, those boxes in purple there, that is the CPU time having to actually churn through the NVIDIA APIs and launch these kernels, and then you see the actual compute time in green there on the GPU. And you know, in this case, like it takes longer to launch the kernels than it actually does to run the kernels. So our GPU's sitting idle for a long time. And wouldn't it be great if we can just launch all of them all at once? Well, that's another good consequence of having the entire graph known at compile time, is that we aren't coming across these operations on the fly dynamically like in Python. We know what we're going to launch ahead of time, so we can basically just gather them up in one big queue, send them all to the GPU at once, and just run them straight through. So that's what we kind of see here with op1, op2, op3. They all share the same command buffer, which is just an Apple term for the structure you use to launch operations. But yeah, they all share the same command buffer. So this was a lot of different optimizations. They are very different from each other. So how do we sort of stay sane here and not lose our minds in complexity? We basically take all these different optimizations, we package them up into their own compilers, and this is, to your point on the different code passes, this is how we do a bunch of different passes. So what you see is like the CUDA compiler, for instance, is made up of a primitive compiler, a special op compiler, a copy compiler, an element fusion compiler. So all of these ones, end to end, you can basically take a bunch of compiler passes, put them in a sequence, and call it a new compiler. And then here's the CUDA compiler. You can see the whole definition, but then On the right-hand side, we actually run a generic compiler before that, which does all those device-agnostic optimizations. So, and what does this get us performance-wise? So Metal obviously received the most attention for us because we are building an app for Mac OS. Metal is the language for Mac OS GPU compute. It's analogous to CUDA on NVIDIA. And yeah, in August of last year, we were at that 2.5 hour per token or something like that. And here was our progress over time as we did a lot of these optimizations. So we're now down to about 25 tokens a second, I believe. So yeah, it's a lot of work. And yeah, we're rapidly catching up on the CUDA side, but there's a lot more stiff competition on the CUDA side because a lot of people have spent a lot of money optimizing them.
So do you compile to CUDA and then cross-compile it to Metal?
No, sorry, so I didn't make that clear. We take the primitive operations that we saw, those 11 different simple operations, and then we can, depending on what we're targeting, run different compilers on that. So we have some compilers that will compile to cuBLAS, and that runs on NVIDIA. We have other compilers, they don't touch cuBLAS, they go a different route, and they compile to Metal-specific code. And Apple also has like a cuBLAS type library, so we can also compile to that as well.
So you take the original and you break it down to 11 primitives, and then from there you can use a specific API of the backend?
Exactly,
Okay.
yeah, yep. And all those compilers are that transformation to the backend.
Are you target AMD devices or general OpenCL devices that are on?
Yeah, so AMD is interesting because cost per flop is actually better. You know, cost per compute is better than NVIDIA because NVIDIA has like an 80% profit margin. Turns out though that their drivers are like not very good. I've heard they're like open sourcing them now and fixing them slowly, but I think we're probably going to wait a little bit until they stabilize somewhat. Unless somebody's like very interested and wants to build out support right now, that would be amazing. But right now, yeah, we're mostly focused on Apple and CUDA. They're definitely coming in the future.
So why not just, like, what you've done with the primitives is really clever, but why not just like wrap PyTorch? Like, what's wrong with PyTorch's primitives?
PyTorch has about 250 primitives.
Okay.
And that's after a big effort to reduce them. They used to have over 2,000. So
Yeah.
it's we could sort of call Torch implementations, but Torch actually isn't much faster at all than us at this point, and so we would just be adding like a really big dependency without much gain.
In the back on the right.
Sure.
Just a quick TLDR. Can you just describe the performance benefits to consumers, to people who are training all that, just like overall, sure maybe you covered it in.
So the question was, can you describe the benefit to consumers? Did I get that? Okay.
Yeah, so we can run, first off, models that couldn't be run reasonably fast on consumer devices. That was the main reason we went out and built this. We wanted to run big models on MacBooks, and so we're able to now run like Llama 8B on MacBooks, and it's fast enough that like you can actually read the words coming out, and it generates faster than you can read. As far as training goes, I'll get into that in a minute, but basically we're able to beat PyTorch native on training speed, so you're able to train on more data in a fixed amount of time, which means your models will be better.
How does that compare against Andre Karpathy's work that he's actively doing right now?
Oh, he blows us away. But the reason why he does is because he's hand tuning LLM.C, which is an amazing piece of work, but it is all done by hand, and so none of that applies to convolution nets or any other type of model but language models. So you can always beat compilers if you write your own assembly by hand. I mean, that's what people did in the 60s. Then people got tired of doing that and they wrote compilers that can do it for them. But it always, I mean, the machines aren't that smart, so it always will be possible to beat them by hand.
Artisanal neural networks. Cool.
Yes.
As a user on Luminal, what's like the learning curve like of choosing the right compilers? Or do you have to make a compiler for yourself? Or
Not if you want to run on the platforms we already support. You can just grab the CUDA compiler if you want to run on NVIDIA, or the Metal compiler if you want to run on Mac, for instance, or the CPU compiler if you want to run on CPU. Those are just available right out of the box.
Is it just like pasting in like the name of the compiler, or is there like is it a difficult process of looking in these compilers?
I wouldn't recommend, just as like from a user, if you don't need to break into the compiler, you probably wouldn't want to. But yeah, it's essentially once you define the graph with those primitive operations and you built that whole primitive graph, running the compilers on that is just one line of code. It's just graph.compile, and then you paste in whatever compiler you want to use, and that gets ran, and then after that, the graph is ready to go.
Does your technology work with state space models such as Mamba? Because it seems like you might be at the end of the road for the large dense GPUs.
So Mamba is, Mamba 2 just came out like yesterday, and it is explicitly built around trying to reformat Mamba into using matrix multiplications because they're very efficient. But basically we support any model that's made up of simple linear algebra, which includes state space models. Mamba 1, for the reasons that they ran into, we would run into the same problems where it's like pretty sparse and it's not very amenable to modern hardware. It would run, but it wouldn't be that fast. Mamba 2, I expect, will be a lot faster, but I haven't tried it personally. So we can also do training. We built this thing as an inference library because we wanted to do fast LLMs on MacBooks, but it turns out that like 6 months after I started, I realized that you can just add training in a very unique way called compilers. You can just run a compiler on the graph, and it does automatic differentiation on the primitive graph, and then creates the gradients, and then you can run an optimizer. You could like basically place an optimizer on the graph, and that'll update your weights. And you can do all of this ahead of time before you run any of the downstream performance compilers. So you basically get all of the compilers we wrote for inference to speed inference up, also now speed training up. We don't have any of this in the core as well. That is another benefit. We're able to add in training as an external dependency. And I don't believe any other deep learning library can ever do that, to my knowledge.
I'm sorry, you on a previous slide showed the acceleration in terms of compute time, and in terms of memory footprint, do you have any kind of comparison?
We don't, but I should make one. It's a fair bit lower. It probably hasn't moved since it said like maybe in February, probably about the same, but you know, we're near the optimal amount of memory usage now, like the physical minimum that you can use. It's actually a lot easier to optimize memory usage than it is to optimize time. Yeah, we're working on benchmarks, so we'll have that in the future. So yeah, we're able to add in training as an external dependency. You can just make your own if you wanted to personally, and we didn't have training, you'd be able to just make your own compiler that adds in training, which, yeah, I don't know of any other library that can do that. And basically, like I said, all the performance compilers carry over to training as well. So that right there on the right is a tweet of mine that basically has the entire AutoGrad engine in one screenshot. For reference, AutoGrad engines are usually in the at least tens of thousands of lines of code. So our extreme simplicity with very few primitive operations allows us to do that in like 150 lines of code.
Do you foresee this being used to do things like federated learning?
Probably. I don't know a ton about federated learning.
Just getting user devices which may not have like a beefy NVIDIA card to help in the training process on the larger models, so they can contribute small, gradients for the bigger model without even necessarily revealing the core data that was used to produce a loss.
Yeah. So we haven't done any work in that direction, but it is possible, and we're actually working right now to, like we said, run LLMs on MacBooks And then if you run, one of the main advantages to running an LLM on your device is that you don't need to trust us with your data. It doesn't matter how sensitive your data is, and it doesn't matter what certifications we have, because you can shut the Wi-Fi off and know that that's never going to leave your device. And so, wouldn't it be great if your models can actually consume and train on that data as well? Well, now that we can do training, we can actually train these models, fine-tune them on your data, on your device, and nobody else is ever going to see that model, and that's not going to ever leak to anybody else. So we're looking at doing edge training, but yeah, I haven't done any federated learning. And so this is basically what we use it for. This is our assistant screenshot on the right here. 8 billion class LLMs on MacBooks at 25 tokens a second. We're able to do on-the-fly code gen. We basically have our assistant in a loop where you talk to it, and it can write code, and it can have thoughts, and it can take actions. We can run Whisper on the same MacBook simultaneously and get 20x real-time performance. So it's near instant. And we're also now using it to do very high throughput synthetic data generation. So like 8 billion class LLMs sound big. They're actually not that big, especially if you want it to be reliable and really, really performant, like high quality outputs. So we have to basically do our own big fine-tuning jobs, and we aren't rich enough to hire an army of humans. So we have to generate all that data synthetically. And so we're also using Luminal to do that on GPU clusters. And all of this is to do a 40-hour work week in 20 minutes and then go to the beach. That's our goal. And what's to come? What's in the future? Well, we're probably going to do more backends. I really like Grok's chips. They seem really interesting. TPUs are cool, except I wish Google would let me buy one. And super optimizers are, to your point about, to the gentleman's point in the back about developing or generating the most optimal code possible. That is what super optimizers do, and essentially what they do is, instead of apply heuristics like we discussed for fusing different operations and doing all these hand-designed compilers, what if we did all the possible operations and treated it, and treated it as a search problem? And we searched in the space of all possible valid equivalent code. And then we just ran it all and saw what ran fastest. And that's essentially what super optimizers do, and that is how people have already designed compilers now to discover things like flash attention and really, really in-depth, complex kernels. So another thing we want to do is distributed training. Like I said, we're going to do large-scale code gen, and we also want to train the models in a very highly distributed fashion. So doing full 3D parallelism, statically validated on the graph, so we can have like copy from device operations on the graph, and we can sort of plan out which data is going to move where around the cluster ahead of time and sort of optimize that. We don't have that yet, but that's definitely a need if you want to train really large models. Reinforcement learning is a area that I'm really excited about, so we want to do RL, and if possible, and I believe it's possible, I don't know, but you could probably move most of the RL environments onto the compute graph and then run them on the same devices that the model itself is running on and training on. And then you can just have an entire RL loop as one static graph completely fused together. So, one of the main bottlenecks in RL, for those unfamiliar, is basically you run the model on the GPU and you run the environment on the CPU. And so every forward pass of the model, then you have to go back to the environment and you have to step the environment forward and get a new observation and a new reward, and then move that all back to the GPU. And so your GPU oftentimes is sitting there completely idle. If we can just put the environment on the GPU as well and compile it all in one graph, the whole thing can go a lot faster. And then, if Sequoia funds us, we'll build a Dyson Sphere. So, yeah, that's what's coming. And come join our cult. So there's the Luminal link. We're really driving into territory that is dominated by frameworks in the millions of lines of code funded by some of the largest companies in the world. and our extreme simplicity allows us to implement a lot of these things that with just a couple people over a weekend that usually would take large engineering teams many weeks. And yeah, if a 40-hour work week is too long for you, you want to cut it down, reach out to me. That's my email, or just come talk to me after. And yeah, we'd be excited to talk to you. And that's it.
What's the difference between this and Torch.compile?
So, like I said, PyTorch has like 250 operations, and Torch.compile is basically trying to do this same approach. But like I said, PyTorch is very dynamic. It approaches the world from a dynamic first perspective, and it has these 250 different operations. And so it has a very large space of necessary optimizations and a very high bar to clear for the complexity of their compiler. And so they've essentially, this Torch.compile isn't the first compiler that PyTorch has done. They've been working on this for like 5 or 6 years now. And Torch.compile is starting to get good, but the wide open nature of PyTorch makes it very difficult to compile down to a very fast representation. They don't put many constraints on themselves at all, and they basically let the programmer do whatever, and then they pay for it in compiler complexity. So by constraining what we allow the developer to do and constraining the complexity of our graphs, we can do a lot more with much simpler compilers.
Yeah. Any support coming for quantized models, especially when
Yeah, so we do intake right now, intake quantization. The only reason we haven't gone to 4-bit quantization is because I'm dubious that there is no quality trade-offs that you have to make. But 4-bit is almost definitely going to be implemented in the same way 8-bit is. We needed that to run fast on MacBooks. And then, you know, who knows, maybe we'll do like 1-bit quantization. But yes, we're absolutely bringing quantization.
Kind of like similar to what you were saying about PyTorch compiler, is it basically the same deal, just to make sure with TensorFlow? And from my understanding, TensorFlow is even a closer comparison since it's static graph. And is it just basically that there's too many data types and operations in their core situation, so it's slower than if you optimize specifically with Luminal?
So today, TensorFlow is almost the same as PyTorch because a lot of people liked PyTorch, and so TensorFlow moved in that direction. But TensorFlow 1, the original one, was static. Sorry.
9 years ago.
9 years ago.
So it was before 1. It was 0.4, 0.6.
Oh, was 1 dynamic?
Sorry?
Was 1 dynamic?
2 is dynamic. So there was, before 1.0, they had like 5 different function calls for the same thing, and it was really messy. And then they got to 1. Yeah, I was going to ask about that. Like, I know it's a little speculative question, but why is it that TensorFlow went the PyTorch route of lazy evaluation and not constructing runtime graphs ahead of time instead of doing something like what you're doing? Because they could have done this like back in the day and maintained some kind of distinction.
They hired super geniuses and figured this out in 2014. They were right. But then PyTorch got really, really popular, and a lot of people were basically coming into the field not knowing like what a static graph was, and PyTorch gave them a very simple interface of, oh, you just do x plus y and you get z. And it happens right there on the fly, and you put print statements in wherever. And so people found TensorFlow to be very difficult to use, and I think from just a popularity perspective, they went the PyTorch route.
Does anyone else here have scar tissue from TF debug? Okay. So debugging TensorFlow, especially before 1.0 or around 1.0, was the bane of my existence for a long time. How does debugging work when someone's using your system?
So we have like dedicated ops that you can put in to just print out the data in tensors, or you can print out, you can basically like diff a tensor with some data you have stored on disk. Debugging will never be as easy as PyTorch. I'm not gonna like sell snake oil here. Dynamism is really nice from a developer experience point of view, but like I said, you really pay for it in terms of compiler complexity.
So how good is NAND detection then? If I get like a NAND or a weird number?
Not very good, but we like to think that we're fairly protected from that because we have a reduced space of possible operators. And so, you know, our operators, they're not generally numerically unstable because we don't have that many of them, and they're pretty easy to just hand check. And then the kernels that our compiler compiles to are pretty well guarded from that because it's like a limited amount of possible kernels that they can generate. But I have had mans in the past, and yeah, in that case, like I just end up printing them out and looking personally. But yeah, I think even installing PyTorch 1.0 probably took a toll on my hairline. So yeah, I hear you there.
I wonder if you could take a tip from what the browser community has done and use source maps. So you know, as soon as you get a man, if you have a map that says this op actually came originally from this line in the Python file, you could at least point someone to the Python code.
Yeah, I think with primitive graphs, that's doable. The problem is that like once you start doing crazy compilation, you don't actually have like an op to line mapping anymore because yeah, you're like you just changed all the ops and there's basically no guarantee anymore that anything relates to anything else that you wrote. This is why I kind of say that eager first sort of dynamic PyTorch style is always going to be easier to debug. And I think the way around this is just making really good debugging tools. So as an example, you're building very complicated models and you're doing a ton of different linear algebra inside it. One of the most common errors you're going to get is shape mismatches because you didn't do a transpose or something, or you didn't feed the right tensor into the right layer, you didn't do some reshaping operation. That's a really common problem, and what I hear. JAX is like the new Google library, and essentially what they've been working on is trying to get the best of both worlds. They have a compiler that is very similar to what Luminal does. It's called XLA, and JAX and TensorFlow now are essentially front ends to XLA. So they basically just compile, they feed all of the neural networks into XLA. XLA compiles and does this whole graph thing, and then spits out some optimized variant. They run that on GPUs and they run that on TPUs and stuff like that. And in fact, PyTorch also has a little bit of support for XLA, but it doesn't work on days that end in Y.
So while we still have, what would be the rough sequence of steps someone would want to take? Let's say there's a model in Hugging Face or just like Llama 3, like roughly step by step, what would they do to have this optimization available for them?
So if you want to export to Onyx and then just import the Onyx graph to Luminal, you can do that. Or what I would personally recommend is you just go to the examples folder and you check out, we have Phi, and we have Llama, and we have Whisper, a couple other models in there implemented, and you'll see that like all this is complicated, but it's all encapsulated inside the compilers. So the actual model code itself looks almost identical to PyTorch. It's a very similar API. And so I would recommend you go there and just check out how transformers are built, transformer or convolutional networks are built. Chances are whatever model you want to run is very similar, maybe even identical. You can just load the weights right into an example.
Yeah, I'm so glad you brought up XLA, because I sat in like a room like not too dissimilar from this 6 or 7 years ago, and Google was like, hey, look, XLA this is the future. And I believed it at the time. I still like believe that compilers will eventually reach that point. But like when I gave up on TensorFlow, like the static graph plus the compiler at the time, it's like the performance just wasn't worth it. So I guess, how do you see XLA and how it's played out? Like how do you see where they're going to be successful where they have?
I don't think XLA is a failure at all because I think it's probably more widely used than, well, it's fairly widely used today. Like I said, TensorFlow is a big failure, I would say. XLA is used in JAX as the underlying runtime of JAX, and so it is still widely used. As we move into this world of more and more specialized hardware, you're going to need to compile to this hardware because the ops are going to get, the operators are going to get more and more esoteric, more and more difficult to write by hand. And so we see a very good example of this with Grok. Grok spent, I believe, the first year of their life just writing a compiler before they even built any hardware. So if you want to target specialized hardware and you want to run it fast, and you don't want to lose your mind with a million lines of code, just sort of like if-elsing and figuring out which kernel to call, you're almost definitely going to need to use a compiler today. So I would say, also like you have like a company like Google, and there is some sort of an amount of bureaucracy and double implementations. And if you ever look at the TensorFlow code, they have like a lot of different things that are implemented 5 different times, and none of them work. So there is an element of that, which is maybe part of why XLA failed. But I think like we can look at PyTorch and the emphasis that they put on torch.compile in their 2.0 announcement to see that this is definitely the path that the industry is going to need to take if they want to keep getting faster.
Yeah, I got a question about flash attention. My understanding is mostly around how can you leverage SRAM, which is the fastest RAM on the NVIDIA GPU. The problem is it's like power hungry, you can really scale these things up. Do you see there's much work into figuring out like how can you make general purpose RAM that quick with these kind of calculations? Or are there other tricks that are coming along that make this a lot harder because now you got to think about like SRAM on board, you have like one chip architecture, like Qualcomm wants to build their own, ARM wants to build their own, you got memory wants to a different flavor of something.
So are you basically asking about something like TensorRT, or is building it for that specific device and that stack? And how could that be like a prioritization scheme for what they're doing?
Yeah, pretty much. Kind of seeing like, what do you see happening there? Is it more towards general compute, optimizing kind of work, and you kind of replicate the magic that flash attention did, or is it more like now you got to keep track of all these different accelerators?
So almost all accelerators work in almost the same way. So it turns out that like all GPU architectures are the same, broadly. They're not exactly the same, but like AMD's GPU is the same as NVIDIA's GPU in all ways that matter. They have their own tensor cores, they renamed them to matrix cores. They have their own SRAM, you want to minimize movement from global. So, I'm sorry, I'm diving really deep in here. For those who don't know, basically the reason why GPUs are fast is because they have many, many processors and they do a lot in parallel. One of the slowest parts of a GPU is reading and writing from global memory, and the reason for that is simply speed of light. It takes a very long time to get the bits from the memory to the compute. And so it's very slow. It's like something like, a read from global memory might be like 50 nanoseconds, which sounds it sounds small, it's not. It takes a long time. But they have local memory that's extremely small, close to the compute units, called SRAM, and that is a lot faster. It's on the order of like 1 nanosecond to read and write to. And so a lot of the process of speeding these models up is basically just how do we move memory, or how do we move less data to and from global memory and more data to and from SRAM. That if you do those optimizations, that applies to NVIDIA GPUs, that applies to AMD GPUs, that applies to Apple GPUs, that probably applies to the Grok chip, although I don't know very much about it. It definitely applies to the GPU. So these sort of broad principles apply across all these different accelerators.
So I didn't know that Grok had their own chip. I thought that they were just doing something similar to what you're doing. I thought they had like an optimized compiler. They have their own accelerator.
Yep, they have their own accelerator. It's really, essentially, how I just said global memory is slow and SRAM is fast. They have no global memory. They do it all on SRAM, and because of that, SRAM is very tiny. You can't fit an entire model on one chip. You need 500 chips to fit a single model on. But if you have a lot of money, you can do 500 chips, and your model will fly, so they can get 500 tokens a second. Yeah, it's all on their own chips, and because it's so special purpose and so fast, they can actually take them out on older process nodes. So it's a lot cheaper per chip to tape out a Grok chip than an NVIDIA chip, especially once you factor in.
Just buying up all this old hardware and reconfiguring it.
Well, I mean, they buy up all this capacity in old fabs, in old factories, yeah. And which are, you know, a 14 nanometer wafer is a lot cheaper than a 3 nanometer wafer. So they can outprice NVIDIA. And I'm sure we're going to see a lot more of that type of strategy.
Is there anything interesting in Mojo, in the language?
Yeah, Mojo, I do have high hopes. I think they took an interesting decision when they did a new language instead of a library, and they you know sort of bit off a whole lot, and we'll see if they can chew it. But they essentially are trying to tackle Turing complete compute. All possible things that can be computed in Python, they have to target and support with their compiler, or they have to fall back to Python's interpreter. And what is actually supported by the compiler versus what needs to fall back to Python's interpreter isn't exactly clear, so if you write the wrong thing in your code, you're gonna go really slow. So, I mean, Chris Lattner, the guy behind Mojo, is a genius, and I wouldn't bet against him, but I do think it's a very, very ambitious, tall order of what they're doing. We take the opposite approach with just trying to do less and less and less, and specify our problem set in a very, very simple, strict way. Constrained way.
When you're talking about eliminating global memory, like what kind of processes are you removing when they use that? Like,
are you talking about the grok?
Anyway, like grok, like what kind of things are normally done in global memory? What things are deep learning?
I mean, storing all the weights they're all stored in global memory traditionally. Now they're storing the weights in local, like SRAM, and because it's so small, they have to spread a model out over 500 chips because of that. But yeah, that's like their own custom chip. I don't know a ton about it. I just read like some Hacker News posts.
So the output, like after you're done with all this, is it executable? It's not like a model file. So like how do you deploy it?
It's a library in Rust, and so if you have a Rust application, you just use this library. It statically links into your binary, and then you just have a binary that you run.
Are there any plans for language support?
We're probably going to do a Python one, but it pains me because Python's a pain to support.
I mean,
But
I can add one thing. It's like in Luminal, there's a server, so you can actually just run the server on the model file, the local server, and so then Python, and it's an OpenAI compatible server. And so if you have like your Python code, you just point it to localhost, and you can just go on
Yeah.
and carry your business.
If it's already targeting OpenAI's API, just target localhost and run the server, and any language will be supported through that.
You support embedding models and LLMs?
Yeah. So embedding models are supported just because they are linear algebra, but embedding models specifically are very sparse because you just have like a huge. Actually, it depends. Are we talking about generating embeddings, or if we're doing like a recommender system, which some people call embeddings? But yeah, if you're doing like a recommender system, they're very sparse, and so maybe Luminal isn't the right choice because it's built for dense compute rather than sparse compute. If you're generating embeddings from a sentence, those are usually just transformers, and so yeah, they're supported and fast. Okay. Yep.
Do you mind explaining when you're talking about the flash RAM part in more of a layman's sense? Like, are you saying that your model is discovering this operation that other people have?
Yeah, flash attention is a mathematically equivalent way to do attention inside a transformer model. It is exact, it's not an approximation, which means it's a drop-in replacement to any transformer, any language model that was trained with the normal attention mechanism. And the main innovation behind flash attention is figuring out how to do everything in one kernel instead of in 3. Because every time you stop a kernel, you have to write the results to memory, and then you start a new kernel. Sorry if you're unfamiliar, kernels are little programs that run on the GPU, and they do different compute.
It's basically like an operation.
Yeah, it's an operation, and every time you stop an operation, you have to write the results to memory, and then you start a new operation, you have to read the results from memory.
and that reading and writing takes a really long time. So what they figured out how to do is put the entire attention layer into one kernel, one operation. So you only read once and you only write once. That was the key optimization. Yeah. Another one in the back. Okay.
Yeah, I was gonna ask, so Luminal attention?
Yeah, I mean, speed of light. Yeah. I mean, someday someday if it goes well, we'll tape out some photonic chips and we'll start doing deep learning on meshes of light. That would be neat.
And then the Dyson sphere, right?
Yeah, maybe that's
To power
before the
everything
Dyson
you're doing.
sphere. I mean, we're going to
Right.
probably have to set up some silicon mines on Mercury first.
Why build a fusion reactor? There's so many out there already, right?
True. That's true. There we go.
Great.
How do you guys make money?
Yeah, so specifically, this is our assistant, this is our program. Basically, Luminal is a library built to support this program, and so Luminal's open source and free, always forever. This program is what we sell, and it's the whole point is to speed up knowledge work. To if you do data entry or just tedious data management, spreadsheets, form filling, that type of stuff, it's able to handle a lot of this, and you can just ask it to, hey, I got this spreadsheet, look in this column, get this data for me. Now, search for all these different, whatever, in this example, stock tickers. Search for all these stock tickers in this bundle of data here, pull out the prices over the last 90 days, and then plot it out on a chart and write that to an Excel file, stuff like that. And because it's so general purpose, it can basically write code out to do these very custom workflows on the fly right in front of you. And because it's running on your laptop, you don't need to trust us with all of that super sensitive data. So yeah, that's essentially our business model. Okay, I think we're.
Thank you so much, Joe. Great. Okay, so we're going to be here until about 8:50. At that point, we're going to head out to Higbee's. It's not even a block away. You can keep networking there as long as you want. I want to give some community announcements. So, Austin Deep Learning is not the only AI group in Austin, but it is the largest in membership and the longest running. So we're 8 years old. If you want to find out other communities that explore different aspects of machine learning, so ours is more about, again, research, getting people to give talks, oftentimes over papers. There's a bunch of others that are about like business applications, end applications, introductions to machine learning, et cetera. If you want to get a good comprehensive overview of that, scan that QR code, join the AITX community. We're also in their community as well. And actually, specifically, they're looking at doing a hackathon soon, I think next month, or at the end of this month. So if you want to sign up for that and give some of your preferences, that's the sign up QR code.
Say a few words on what a hackathon is.
Sure. Yeah, so hackathon is, you show up, you form like a little team with a couple people, and you tackle a project or a problem. The goal is to have a space where you can quickly collaborate. You don't have to go get Zoom fatigue and Slack. You're just right next, shoulder to shoulder with a bunch of smart people across varying levels of skill sets. So if you're new, you can usually find people that are also all on that line. You can learn together. If you're a little bit more experienced, it's also a great place to network.
Mind going back to that first code again?
This one?
Yeah.
Sure. So this is just a general newsletter. Give you all a few seconds. Okay. And then this is specifically to sign up for the hackathon.
So a couple of more things from the hackathon. So often there are multiple days. So people just show up, sometimes with an idea, so normally these can be a couple days, people show up, you don't necessarily need an idea, people do pick up teams and kind of put something together, demo over the weekend often. So if you want to do that, you can sign up. Also, they're going to need mentors and technical advisors. And so if you're interested in just spending a couple hours to aid these teams, I would also go sign up and say, hey, I'm happy to talk about technical stuff or business advice or anything. So it'll be a community event. So if you're interested, sign up and see how you want to participate.
Here, Jason, did you want to say anything?
No, I think that's great. Definitely check out the Discord if you're not on there already.
we'll post, links to all the content.
Yes, he has the link for the Discord. So yeah, we're also deep learning, mostly focused on breakthroughs, research, and also community. So I'm gonna stop here, and y'all can mingle with each other. There's a lot of bright minds here. And thanks again to Capital Factory for always hosting us. So, thank you.
What is it that you're selling? How much do like actual companies care about? Great. Okay, I mean, yeah, there's a selection bias. I just like, I like the open source a little bit. The only reason I ask that is that like every entrepreneur says that customers care about privacy, and then the moment you make them a product, they stop caring about privacy. And so I don't know how much like in making demand there's going to be for open source outside of the well, yeah, so I don't know how so I was wondering what happens. Specifically, corporations are unique in the sense that they have their traceability.
Yeah, there's actually a lot more you can do after the